Okay, so welcome back to the possibly the last lecture for the week, and this is on the memory map layout of ARM Cortex M0 Plus. So we did discuss about the internal components of the ARM Cortex M0 Plus, and then some detailed discussion on the register map, register bank, and then now we will discuss on the memory map. And please remember, this is actually outside of the processor core or processor chip. This is actually more of a peripheral device, but ARM has done in such a way that we could actually leverage this arrangement unless we want to tweak with it. But this is good thing about this is actually we can straight away start the programming, okay, because the locations are mapped and microprocessor knows when you give a certain location, it knows where to look for, okay. So that's the concept. So just to brief, I have very high level overview of what we have is like 4 GB of memory space. That's huge, right? And I'm talking about something in the range of 1000 to 1500 rupees. And if somebody is providing you this much, that's enormous, right? So this is something which is very significant. And then of course, as I said, I think we briefly saw the memory map layout for Cortex M0 Plus. The 4 GB space is actually divided into a number of regions predefined by ARM. You can obviously change it, but I suggest not to alter with it because it's quite optimized and you can directly start using it. Okay, so each region, so basically the 4 GB for the microprocessor, it looks like 4 GB continuous memory. But please remember the layout is like the individual memories will be of a particular type like flash or RAM or ROM or whatever. But they are physically also located at different places, but they are arranged like the tutorial that we did. For the microprocessor, it looks like a continuous 4 GB of address locations or memory locations rather. Okay. And then, yeah, this is what I said. Despite the default memory map, there is a provision to define the map by the user. But that's like a lot of tasks. And if you're very particular and there is a reason for you to do it, please go ahead and do it. Otherwise, please go ahead with the map which is given by default by ARM. Okay, so that's the thing that we generally prefer. Okay, so that's the scenario, and this is sort of more details. Actually, we will have exact layout map in the next slide, but I thought I'll gradually introduce to you some concepts here. I think some of them I already introduced to you, so it's just like a repeat, but it's always good because we are learning this first and then you should know it in a bit thorough way. So each, of course, I think all these things you already know because you had a hands-on. So each memory location has an address, and this is very important. This is specific to Cortex M0 Plus, so you have to be careful if you choose a new microprocessor. Please see this. So each location is something like 8 bits, you could say. So that is the concept here. So it's a byte addressable. Each location holds a byte. So for example, this is just to give a feel for it. So let's say one location which is given by this address, it has 0x70. That means this holds an 8-bit data which is decimal is equivalent to 1112. Okay, so some layout, I mean some sort of representation is shown here. So the size, so each location holds 8 bits. Please remember this, okay? And we know that we do Cortex M0 Plus bus is 32 bits, so it can handle 32 bits of data. So that means you need to consider 4 locations together as a data. So that is the meaning of it, right? So 8 bits, 8 bits, 8 bits, 8 bits, they make 32 bits, and that forms a data for a Cortex M0 Plus. So very important. So if it's a 16-bit instruction, that means two locations is what you are interested in. Okay, and then number of locations, how many locations do you have a 4 GB? You already know it's 4 GB, but how literally how many locations it has? So the calculation is something like this. We know 1 KB is 2 raised to 10, so 1 GB is something like 2 raised to 30, right? And then 4 GB means 2 raised to 2 into 2 raised to 30, that is 2 raised to 32. So 2 raised to 32 locations, very important, okay? So this goes, so basically when we say 2 raised to 30, that bytes is for the location, okay? So this, each location has 8 bits, so that's the meaning of it. So 2 raised to 32 locations will amount to this many locations for you. So that's the concept that should be the takeaway for you, okay? So very important. So it's enormous, right? So many locations of data, and each location is 8 bits is the meaning of this. Okay, so the values inside, so we are following the von Neumann architecture. So the same memory will be used for storing data as well as this one program instructions. So that's what the literal meaning of this statement. Okay, so hope it's clear. There's nothing major confusing part here. And so if you want to really map the address location, it goes all the way from 0x0. So this is basically representing the total 32 bits, right? The address locations are 32 bits. That's what it represents. Okay, and then it ranges from all zeros to all F. That's the thing. And this is the exact layout. Of course, no need to by heart. This document should be there with you. I will give the reference when the lab starts, so you can follow them and keep those documents ready with you, or you can even take the slides with you all the time so that it's crystal clear. So remember, the start address is this, end address is this, and among them various types of memories are there. But for microprocessor, it appears to be a continuous address location starting from this to this. And among this, there are specific use cases for different memories. So this is the code memory, which will be mostly flash, and this will be on chip. So there's no interfacing happening here. And then it ranges around 512 MB of code memory. Okay, so important thing is like this cannot be changed on the fly. So this is like you program whatever you want to do with the microprocessor priori and store it in flash, then you switch on or restart your microprocessor. This will be executed one after the other. That is the meaning of it. Okay, and the important thing actually is this concept. I think one interesting aspect, another important aspect is within this code memory. So somewhere around 128 KB is flash. Remaining is actually like part of we can call SRAM, something like that. Okay. So because you can see it over here. So this range is actually SRAM. So this part is actually SRAM, and this part, the first part 0 to up to this location is flash. So flash is where you generally store your startup code and all those aspects. And then this part you can use it for RAM. And then there is a dedicated space for data memory if you want. That doesn't mean that you can't store data in this space. You can do that. But there is one dedicated space which is around 512 MB where you have your RAM. And inside this you will see later it will be divided into something like stack, heap, etc. Okay, so then after that you have around 512 MB of peripheral which is dedicated to the bus registers. So basically, as I think I mentioned it many times before, for a microprocessor, everything, even if it's a component, a device, and a peripheral device, it looks like a memory location, and that's what the meaning of it. So there will be, when you study about the interfacing there, you will understand this. But at this point, you can think of even the buses will look like registers, and those registers are look like memory for the microprocessor. So this is around 512 MB. And then external RAM, this is to connect your LCD or your external DDR memory, flash memory, etc. That is huge, 1 GB of that. And then of course there is external device like SD card, which is again 1 GB. So total 2 GB of external memory you can actually connect. And the important thing is this is connected through this bus. So there will be some delay. It won't be as fast as this because most of them are on chip, you can say. You can see that. So this doesn't look like an interface. It is connected on the chip, but these two are like interface. So there will be more delay associated with this compared to accessing from these locations. And then the some peripheral bus, which includes the control space, system control space, and the interrupt controller, everything. Those registers are sitting here in this location. And then of course some space is reserved for the system, which is like the BIOS in our computer. And together they occupy 512 MB. So the overall idea is like there is a huge chunk of 4 GB of memory which is divided and mapped for you by ARM, which can be changed by you, the layout. But literally it means like microprocessor sees like continuous chunk of memory starting from all zeros to all F, 4 GB of memory. And the idea about dividing them into small spaces is like the user, whoever is going to program, is crystal clear about what to look for or which memory to access for when he writes the code. Okay, so there is a understanding here. So this I will skip because whatever I explained is actually detailed here. This is for your reading, so I'll just leave it. If you have any questions, we can take it up later. So Even though for the microprocessor it looks like a one series of locations arranged together, it doesn't is in the physical case because it is distributed. You can see over here the peripheral memory, the system control space, NBIC and all those peripheral bus, all those things are located inside the processor core like this. Then you have the bus memory, which is actually like outside of the processor chip. And then when I say processor chip is different than the chip, right? So this itself, this box that you're seeing over here itself is a chip, and inside that there is a processor chip as well. Okay, so this is like system on chip, you could say. Okay, and you have a flash memory on chip, RAM, etc. This also we saw in the memory. Then you have the peripherals like timers, the serial interfaces, which you will study. All these things you will study later. And then of course the external, which is not inside the system on chip, which is to be connected from outside like LCD or SD card or external SRAM, flash, etc. through the peripheral device interfaces. So this again is the memory. So whatever you see, so this block, this block, this block, this block, and these two blocks are all in that memory layout. So for microprocessor, it appears to be like a continuous chunk of locations. It just reads and writes to those locations, and those locations are physically connected to these different parts, different devices using the digital circuits. So that's the idea. So I hope I'm not confusing, but it should be very clear in your mind that even though memory things are everything are outside, for microprocessor everything is a memory and looks like continuous locations of memory. 4 GB, just have that figure in your mind. Okay, moving forward. Some example. Okay, so this is something which is I just purposefully do it just to deviate, and otherwise it's terribly boring if I continuously impart concepts on you. It's really boring. Ideally speaking, this course should be like along with the board in your hand. Unfortunately, our situation doesn't allow that, but it's okay to do this. So let's say you write a C code. This code is very familiar to you. In the class, it would have stopped and asked you what is the functionality of this code. It's pretty simple. It's a counter. You can see it over here. So you are initializing a counter and then of course an array, and then you are initializing another variable I, which is going to be used frequently. Another variable B, which is again like an array, but again this is initialized. So this two we can assume to be 0 initialized. This is initialized with some values. This is like something which is again 0 initialized, but it is going to be used many times. So I'm saying all this because you should know where it is supposed to be stored. So where this counter will be stored, where this A will be stored, where this I will be stored, where this B will be stored. Okay, and then of course we do this operation. The I has to be incremented, and then you store the value. You take one by one the values of A, and you increment that counter 5 times. Okay, so that's the idea. 5 in the sense like all these values are, you just increment these values by 1. That's the meaning, right? So, and the counter, actually interestingly, counter will give you, what is the value of counter? It will be just 5 in this case, right? So because you are just incrementing it as many times. Okay, so that's the idea. And we are not worried about functionality of the code anymore, just worried about where these variables will be stored in the memory map. If you would have used Cortex M0 Plus, where these variables would have stored, because everything should look like a memory location for you, right? There is no variable name or anything which computer understands. The processor only understands this as memory location. So let's start with so this is the general layout, a very generic layout. So you will have the instruction memory. Typically you put them in the flash, and then you have the data memory. Typically you put them in the RAM. And then in the RAM itself, this is what I was telling you in the previous slide also. This is split into different types. So you will have the initialized data. That means it is not 0 initialized. Then you have the 0 initialized data here. And then you have 2 important types of data memory. One is known as the stack, and the other one is known as the heap. I think I told you before also, stack is like an orderly arrangement, as the name suggests. It's a stacked arrangement. So something like first in, last out. Okay, so if you put, so it's actually starts from some initial memory, which is a higher memory, and if I add the data, the memory location is decremented. Typically the memory location is incremented, but in the case of a stack, it is like top to bottom approach. So you keep on storing data from top, and then in that sense the memory location is sort of decremented. It grows down. Heap actually is an irregular arrangement. It's like you can access any location, there is no problem, Heap is just like any other memory, the address grows actually. So just from a lower address to higher address it goes. Okay, so this is the concept. And now let's say counter, let's say where it is going to be stored. So counter, as I said, when I say in counter, it's automatically initialized with 0. So it goes to the 0 initialized data part. And A is initialized with some value, so it will be going to this part. And what about I? Where will I go? So as I said, I is going to be used frequently, like here, right? Here it is used and here it is used. So if any variable is going to be used frequently, it's always better to avoid the bottleneck by storing them in registers. Because if you store them in registers, you can actually no need to load them from memory all the time, right? And you are going to be used. So this will be not be stored in memory. This will be stored in registers. And who will decide all this is your compiler. So as a user, you have no role here, but I just giving you an intuition. Okay. So you should also be thinking this way. So this will be stored in registers, and this will be decided by the compiler itself. You don't need to decide. Okay. But I'm just throwing some insights. And then of course B of I is again going to be initialized, but here it is not going to be initialized as 0 because it is an array. So array means it's like a stack of memory, that is why it's going to be here. And then of course the instruction as such, instruction only, not the variables, will go to the instruction memory. Another example, so this is a pointer, and that is actually, so pointer is like again like a sequential arrangement of memory, so it goes to stack. And then bool also, it's like most of the time this bool B will go to stack, and then this also will go to stack, one after the other. And then this pointer, because you can actually define this particular character 500 thing generally. I mean, this is from the way a compiler works. There's no hard and fast rule that every time it works this accordingly, but this is just like from an illustration, just to give a feel for you. This is how typically things work. Okay, so it may change, it depends on the compiler. So this is just an illustrative example. It's not like a hard and fast rule saying that this is the only way possible. Okay, some these things you can ignore. I think this is more for advanced stuff. I took from an advanced course, so that's why it's here. But the more important is this concept. The stack is an orderly arrangement, so you keep on top, and then of course you may not be able to take this out. Take this guy out before taking the top guys out. So first in, last out is the concept. So you add the, let me just use the pointer. Yeah. So you start with this, you add here, then you add here, then you add here, then you add here, and then if you want to take this data out, you need to actually take these, take this data out, you need to take these three data out, so that you can take this. So there is an orderly way you take it out. And we will again revisit the stack when we learn a particular instruction, which is push and pop. Very, very interesting application. That time we will again revisit the stack and you will understand it very thoroughly. And anyway, you will be playing with this in the lab also. So don't need to worry. Heap doesn't matter where you store, you can access that anytime. Okay, so that's the random access sort of. Okay, so a trivia, I would have stopped in the class and asked this question. So what are the memory address of these 4 words? Okay, so when we say word, it's like 32 bits. Okay, so this is one word which is 32 bits. So each location is 8 bits. So you need 4 locations for storing them. So what will be the address for this particular 4 blocks of data, which is 32-bit data? So the answer is very simple. We will have that concept clear when we talk about Endianness. Okay, so it's coming in the next few slides. But just wanted to let you know that the address will be actually these 4 guys. Okay. Okay, so I'll just tell the values here so you can see it over here. Let me just discard. Okay, so this is the address. So basically this points to this guy, this points to this guy. So starting of the 4 bits will form the address. Very simple. Okay, so now you can argue me, very, very important, why don't this be the address? So it depends on something which the processor follows, which is known as Endianness, which we will discuss in the subsequent slides. Okay, so this is what that concept is. So Endianness, actually Indian refers to the order of bytes stored in memory. Okay, so there are 2 types of Endianness. This is all coming from the Gulliver's story, if you remember the Smurfs and the big guys story. So little Endian and big Endian is the naming inspired from that. Okay, so little Indian, if the processor is following little Indian, okay, this means the lowest byte of a word size data is stored in bit 0 to bit 7. Okay, so that's the thing. So if we have a data, 32-bit data, it will be composed of 8 bits, so like 4 into 8 bits, right? 4 locations it takes, and the lowest byte will be actually stored in bit 0 to bit 7. That is the concept. So most significant byte and least significant byte, that's a confusion that we are having. So you have basically, let me put it this way. Okay, so you have 0x, so I'll just put x for illustration. So this is basically 4 bits. Let me just put. So this is 1 byte, 2 bytes, 3 bytes, 4 bytes, right? This is the arrangement. So this the most significant byte in the data, or this is the most significant byte in the data? So that is the confusion. So if it is little Indian, the lowest byte will be stored in bit 0 to 7. So this will be LSB for the case of little Indian, and this will be MSB. But if it's big Indian, lowest byte will be stored in 24 to 31. That is this guy's 24 to 31. So if it is little Indian, this is the concept. Okay, so for the little Indian, for the big Indian, this will be the concept, which means this will be the MSB and this will be the LSB. So that is the concept. But Cortex M0 Plus actually supports both of them, both little Indian and big Indian. And one important thing is like Endianness only exists in the hardware level, right? Because you are storing it in some way. That's the only place it exists. So just to reiterate again, little Indian means, I always remember, there's a confusion how to remember this. Little Indian means little. Little means lowest byte at lowest location. That's the meaning of it. So you can say byte 0 is here, byte 1 is here, byte 2 is here, byte 3 is here. So that's the concept. So you can actually see. So 7:0 has the byte 0. And 31:24 has the byte 3. So most significant byte sits at the most significant locations. Big Indian means the opposite of it. So the little guy will sit at the significant bits at 31 to 24 and reverse. Okay, so little. That's the only thing that you have to remember. Okay, so where it comes from, some inspiration from history. The Jonathan Swift's famous novel Gulliver's Travels. So this Indian concept is actually, this concept is actually taken from there. Okay, so I'm not joking, it is actually true. And IEEE Computer Society, they published this standard so that everyone follows this. It's very important for this to be specified in the document of your reference document of your processor. Okay, so that's proposed by famous engineer named Danny Cohen in 1981. After that, every company literally follows this concept. Okay, so example. Okay, so here you have a variable which is 32-bit is something like this. Okay, so if where this will be stored if it is little Indian. Okay, so this is the value. So basically the address location, we already know that it will be starting from 0x0000 up to 0x004. Right, 1, 2, 3, 4. Okay, so you can see this 78 is the least significant bit, it comes first. Okay, so that is the concept. Okay, so least significant byte at the least address, and then it goes, then it goes, then it goes. So big Indian is just the opposite of it. Okay, I think it's not much confusing, so I'll have a trivia here so it makes very clear for you. Okay, so this is the word that you want to store, and this is the address location. So how will it get stored if it's a big Indian? Okay, so big Indian means lower significant byte should go, or more significant byte should go to the lowest bit, right? So this is how it gets stored. So here the more significant byte is this guy EE, so that goes to the lowest address, and this is the least significant byte that goes to the top address. So just the reverse. So typically this would have been starting here, and this would have been ending here, that is little Indian, but big Indian is the opposite. So least significant should be last, or the latest address should have the least significant. That's the meaning of it. And then the other way, if it is I think a small typo here. So if it is little Indian, let me correct it now itself. Okay, so if little Indian would have been there, the least significant bit is in the lowest address, and most significant byte is in the most significant address or the top address. That's the meaning. Okay, so that's a typical. So if we go back to my one of my previous slide, okay, let me just go back there. Yeah, I think this one. Yeah. So here, this is entire word, right? 32 bits, and here the address is this. So this is basically the starting address, and then or maybe we'll start from here. So 0001 123. So I didn't mention anything on the content here. So based on this content, you will decide whether it's a little Indian or big Indian, or you put it the other way. You are known that this follows the concept of little Indian. Let's say this is actually following the little Indian concept. So then how would have been the situation here? So let me just use it. So if it was following the little Indian concept, so then this would have been what? This would have been MSB, right? The most significant byte of your data, and this would have been LSB. And if it is big Indian, it is just the reverse. So that's the concept. Okay, so let's move on. Okay, so it's done. Again, one more time I'm just writing, but it's the same. Okay, so yeah, so that part is done. The memory map. Now a small deviation, but this is also very important. So we should always know, this is very specific to our processor. Okay, whatever I'm going to talk about from now onwards will be specific to Cortex M0 Plus. But these concepts are very similar if you choose another microprocessor. It doesn't matter ARM, any other microprocessor also. The more or less the concepts remain same. So you can easily. That's why we choose one processor and study it in depth. Then once you do that, you taking another processor and expanding your knowledge or expanding your expertise to that is like just straightforward. Okay, not very difficult task. So the program image, so this is actually the code region. Okay, if you go back to the memory map and see, this is actually the code region in the memory, and that is actually divided into some small parts. There is a vector table, which is actually defining certain address locations, which is predefined and stored for you, something like this. So the initial stack pointer, then there is a reset vector. So this is addresses. Okay, all these are addresses, which are again addresses pointing to some in this region itself. So this is an address which is having the stack pointer location. This is having a reset vector, so that is where the program is going to get started with. And then there is a non-maskable interrupt location, then hard fault interrupt location, there's some reserved space, then so many other things. So all these things we will discuss later, okay, at this point. So, but you can imagine there is initial some space which is actually reserved for some address locations. And then your startup code. So whenever you press the reset button or whenever power on the system, the startup code will actually be located at this reset vector location, and then it will get executed one after the other. Okay, so that is the idea. So whenever you use the board for programming, you use a software named as Keel Microvision. So you write the program there, and then that code will be actually going and sitting in this space. Okay, so that's it. Hope it's not very confusing. If it's confusing, don't worry, because you will do it and you will come to know about it in a much better way. Okay, so this is the way our Cortex M0 Plus starts. Okay, so very, very important to understand this concept. Okay, so how does it start is actually it after the reset, the processor actually it's shown here. So let's not read out, it's much easier to understand from this block diagram. So this is what's going to, please listen here everyone, don't deviate from this, because this is what you're going to experience in the lab. So you press the reset button, you did the program, of course you use the software, you write your program in assembly language or C language, whichever language, and then you burn that to the microprocessor, just like we generally do for any processor or any FPGA or any digital system, any software driven digital system. And then you press the reset button. What is going to happen is it will fetch initial value for the stack pointer. Okay, so that's the thing. So that is the address. So basically whatever is the content in this guy will be the initial value. So you have a chance to set that also if you want, because you define the stack space and you can actually put that initial value of your stack pointer there. Okay, and then it fetches the reset vector. So the reset vector is actually this particular address location. Okay, because remember it is 32 bits, that's why an increment of 4 you are seeing, because each location is 8 bits. So there is a content that you can write. So that is the reset vector address. So that is what you want to put in this particular location. That will be read. So your program, whatever you are going to write, will be put in this location. Okay, reset vector location. And then fetch first instruction. So that means whatever content is in this reset vector, that is your first instruction. So that is done. Then it goes to second instruction, and it just continues in this mode known as thread mode until an interrupt happens. So interrupt is something which we briefly discussed, and we will go in detail. There is a dedicated lecture for that, so that will come later. But this is how typically it happens for you. Okay, so that's it. I think pretty much done, and then the next view is just an illustration. Okay, so the reset button, the initial is the stack pointer address, then the reset vector address, and whatever you return in that reset vector address will be executed. So that's the literal way it happens. Okay, so we will stop this lecture with a very brief discussion, illustration of some example of how what will happen inside the hardware, which is already known to you. This is like again a review. Okay, so you have the register bank. So this is the processor code. You have the ALU here, and then you have the register bank. All our registers sitting here. 3 of them are the special registers, you could say. Okay. So R0 to R12, the 13 of them are general purpose. Out of that, we always remember that R0 to R7. Only if it's not generally accessible to everyone. Okay, so let's actually do it. So this is the memory which is sitting outside the chip, and it may be inside the system on chip. For example, the freedom board that you have, it may be together one chip. Okay, and then these are the locations starting from all zeros to all F. You have some data in these locations. Okay, so let's do some example. Okay, so fetch instruction. So this location, address location, whatever is the instruction. So this is just an illustration. Okay, you will understand this more when you do that, but I just wanted to. So this address location has 2100, and 2100 literally means move S R1 hash 0x00. This means, again, instructions we have not studied. So we will study that in detail in the next week, where you study about the bunch of instructions, around 56 of them, that the ARM Cortex M0 Plus supports. One of them is this move S operation. So this means move with sign bit included. Whatever the value that you're going to choose is this value to register R1. So this is a literal meaning of this. So if I execute this instruction, what is going to happen is, okay, so the program counter of course will have this address so that it can execute this particular instruction, and that instruction means move RS, that means move S R1. So to register R1 you move this content, that is the meaning of it. So what is going to happen is this location will get the value 0x00, and in binaries it looks like this. Okay, now another instruction. So let's say this instruction 2201, it means R2 will be stored with this. Okay, so that means literally R2 will be stored with this value, and then add as R3, R1, R2. That means add R1 plus R2 and store that result in R3. So these two contents will be inputs to the ALU. Output will be actually stored in R3. Okay, add with sign, that is the meaning of this. Anyway, these expansions, details, everything we will discuss later, so don't worry. So that's it. Okay, done. So we are all set. So this particular week what we did is actually we understood the architecture of ARM Cortex M0 Plus. We also had a deep dive into the register layout, then the memory layout, and then typically what happens when you press the reset button. So all these things we discussed, but as we know that we are not going to work on the hardware level of the Cortex M0 Plus, or for that matter any microprocessor, because that is done by the vendor, done by the company. All our concentration is on to use them, and to use them you need to have some understanding, which we did in this week. Next week we will more understand about the instructions, and then we will make use of those instructions to come up with some programs. So that's the idea. So we'll start with some typical programs which is just within that microprocessor. No interfaces or any communication with the outside world is done, and then slowly we will learn about these outside communication things and move on. Okay, so that's the way we will proceed in this course. Okay, so with that this week is completed. Please go through these lectures and again, and any questions please feel free to raise them in the discussion. Okay, so thank you, and looking forward to seeing you all in the next week.